We're starting section 15.2, limits and continuity in several variables. So limit of functions of two variables. Let f of x and y be a function of two variables. The statement limit as point x and y goes to point a and b of f of x and y equal to L means the closer the point x and y gets to a and b, the closer f of x and y, which is a scalar, gets to L. Or as the distance between x and y, points x and y and a and b approaches 0, so does the difference between f of x and y and L. And so for points it's distance, and again input is not one single variable, it's multiple variables, so you have to think about the distance between 2 points, and the output is a single variable, so the difference between the output approaches 0. We can make the value f of x and y as close to L as we like by requiring that x and y is sufficiently close to a and b. So basically I can choose how close f of x and y wants to be to L, as x and b is close to a and b. Multivariable limits are more complex than single variable limits because x and y can approach a and b from many possible directions, not just two. In single variable you would have limit as x approaches to a value from left or right, right? Here the x and y can approach a and b from all sort of directions, and it doesn't have to be straight line, and all of that, and still we have to get same result for all of them. So what do we mean when we say multivariable limits can be more complex than single variable limits, because x and y can approach a and b from multiple directions, not just two. Here's the example. See, this point, the black, is point a and b. Then you can, and the directions that you have to watch out for can look like this, can look like this, can be straight line, can be wiggly line, and basically in any path you can approach the point, and still you have to the z value for all those paths should be basically approaching the z value of a and b. So z value for any points on these paths should be, as it gets closer and closer to a and b, should approach the z value of a and b, basically. So for the limit of f to exist at a and b and equal to a L, the values of f of x and y must approach L on all these curves and infinitely many others. So basically on all of the curves variable. Okay, so let's now express this. We're discussing, first of all, we want to go back to the notation. The notation is limit as x and y approach a and b of f of x and y is equal to L. This means, so this is a multivariable notation for limits. This means that limit as of f of parameterized xt and yt approaches to L as t approaches to c for all parametric curves x of t and y of t, for which this t approaching c of x of t and y of t gives you a and b. So the significance is that you're thinking about multivariable curves, multivariable notation of limits, and then you're saying, okay, so multivariable notation of limit means there's infinitely many limits in single variable. So that's the significance of how this limit in multivariable works. Of course, we can't check infinitely many paths, so that's not what we're expecting you to do. So we're going to give you some tools to actually compute these. Tools, this first set of tools, and as we did in single variable, first we give you, well, what if we have just normal functions within the domain? What do we call them? Do we call them elementary functions? What is it? What if everything is just a composition of elementary functions? And so this slide, limits and continuity in two variables. The limit laws, Rogowski and chapter 2.3 has it, still applies to limits in two variables. As you remember, what we discussed a little bit in 15.1, we discussed how the functions, the outer function can be even a single variable function, and so on and so forth. Now, if the same laws are satisfied, the sum law is satisfied, product law satisfied, power or root laws are satisfied, constant multiple laws are satisfied, and quotient laws are satisfied. Again, if the limits, let's say limits of two different functions exist at some point, the sum of the two functions has a limit at that point. If the limit of two functions exists at a point, the product of the two functions have a limit at that point, and so on and so forth. Now, we say that z equal to f of x and y is continuous at a point a and b if the limit of a limit as x and y approach point x and y approaches a and b of f of x and y is equal to the value of f at a and b, f of a and b. So it's again limit as approaches to a and b is equal to the value of function at a and b. Now, what does it mean that function is continuous on a domain? We say that z equal to f of x and y is continuous on a domain if it is continuous at every point in that domain. Very similar to calculus of one variable. Continuity of elementary functions, just like calculus 1, there is good news. Elementary functions are continuous on their domains. An elementary function is one that can be constructed from building blocks like polynomials, rational functions, root functions, exponentials, logarithmic, trigonometric, and inverse trig functions using the arithmetic operation and function compositions. And so basically just take him and any finite number of those is going to give you an elementary function. Example, limit as x and y approaches -2 and 1 of quotient 2x squared over 4x plus y is equal to -8/7. How does this work? Remember, this function, what is the function? Function is 2x squared over 4x plus y. So the function is this function, and the function part of the domain, see, -2 and 1 is part of the domain because if I plug in -2 and 1, -2 for x and 1 for y, it's defined. The function is defined, and rational functions are supposed to be the domain of rational functions is where they are defined. So what do? I just do direct substitution as we did in 2.3. Direct substitution, put in -2 for x, 2 times -2 to power 2, and 4 times -2, and 1 for y, and then compute, and you end up with -8, 7. Example 2, limit as x and y approaches 2 and 4 of y arc sine of x over y to power x is equal to, let's see, if is 2 and 4 part of the domain, does it bother x and y? If I put in 2 for x, 4 for y, I get 1/2. Arc sine of 1/2 is defined. Here multiplied by 4, it's defined. To power 2, it's all defined. So 2 and 4 is in the domain of this function. Therefore, all I need to do is to plug in 2 and 4 in the function. 2 for x, here it goes 2 and 4 and 4, and you compute, and you end up with 4 pi squared over 9. I calculate question 15.2a. If limit as u approaches 0 from right side, g of u is equal to L, and f of x and y is equal to g of square root of x squared plus y squared, then limit as x and y approaches 0 and 0 of f of x and y is equal to L. Take a moment and come back. So hopefully you solved it. And so again, the outer function here is a function of single variable, and just like we saw in a few examples in 15.1. So g is single variable function, and then we're basically seems like if you find the limit of g as u approaches 0 from the right side, you get L. And here, what is inside here is an elementary function, and limits of that as, so limits of, let me write this down, limits as x and y approaches 0 and 0 of x squared plus y squared, since 0 and 0 is part of the domain, is going to be 0. And not only that, it's basically gives you positive, it approaches 0 from positive side. And so over here I can replace it and say that since f is g of this function, basically use the composition and say that it is true.